We're moving on to this problem here. We'll see whether this thing places it actually. We'll actually put it in the right spot. There it is. I'm going to go with a new layer. Alright, so now here's what you've got. This is a 3D problem, and what you've got is something has a 5-foot diameter, so the radius equals 2.5. 4-foot height, and it's 3/4 full, so we basically have 3 feet height. And so the volume is pi r squared times h, which is 3. And that's going to give unit weight times volume is going to be equal to the weight. So that's going to be what's pulling up. So that's how you go about doing that. You need to know how to do a volume problem. You're going to take the weight, and that's going to be the knowns, if you would. Now, we also now know that we have, if you look from the top, we've got a chord here at 15 degrees, right? We have another one at 90 degrees, and another one at 240, that's 180, and so this one here is going to be there. So you've got those three coming up to a spot there, which is above. So what are the locations of that? Well, if it was a unit circle, this would have coordinates of, at 15 degrees, think about it, it would be 2, 4, 6 plus the square root here, and 2, 4, 6 with a minus there, over there. That's the two coordinates. That is if it was a unit circle, and then you're going to multiply it by 2.5. At the top here, obviously, it will have coordinates of 0 and 1. Multiply that by 2.5. And here, you're at 240, which is 60 degrees down, which is the same as 30 degrees here. So you're going to look for the 30-degree value, but you're going to flip them. The 30-degree value, so you're going to say 1/2. And the x, it's a minus, and minus the square root of 3/2. And that's also going to be equal, multiply by 2.5. So you've got coordinates of that point, and that point, if you would. And then you also have this fact, if we're going to call those all at elevation 0, and we also have the z elevation, so the elevation of these is equal to 0, and the elevation at the top is going to be equal to 5. And if you think about it, that 5 is going to have elevation coordinates of 0, 0, 5. And so now you have a vector that's going to describe from that direction to that direction, that direction to that direction to that direction to that direction. You have all that, and now you can actually solve it by writing. We'll call this tension 1, tension 2, and tension 3. By writing this equals the opposite of the known. So we're going to go ahead and realize we'll call that T1, T2, and T3. We will have this direction, right, which is essentially going to be some multiplication, etc. This is going to be the direction. So the direction of T1 down there, the direction of T2 down there, and the direction of T3 down there. In other words, the x, the y, and the z component as it goes down this way. And if you're looking at that point, you've got essentially weight acting up this way, and then these wires coming down something like this. So weight is going to be then that negative value here of weight. It's going to be going down in the z direction. Again, looking at that as was described. So understanding that if you've got a 3 unknown wire problem with known directions, you put the direction, they're called the direction cosines actually, and what they are is the vector dot product with basically the I, the vector dot product with j vector, and the vector dot product with k. Essentially what they are, of course, are the three components of the vector divided by its magnitude, the length divided by its magnitude, and we'll work that out and put it out on a solution set. So Once again, understanding here that you need to get a volume times a unit weight equals a weight. Who put the unit and unit weight? The unit, a volume did. So we have a volume here. You could also have done it compare and square. This is a 4 foot compared to a 2 foot is 2.5 squared, which is 6.25 times pi times 3, or that's about 20 pi cubic feet times 62.4, etc., etc. So realizing that both the 2D problem, which is tension 1, tension 2, and then some other value there, is a matrix problem, and this 3D is a matrix problem as well, becomes incredibly important. You just then need to realize that you need to break up any direction or any wire into its magnitude and its direction. And the direction, of course, is the vector divided by the magnitude. The vector in the y component divided by the magnitude, and the vector in the z component divided by the magnitude. That is going to help you a lot to very quickly understand what you plug into these direction vectors. They're called the direction cosines. All right, so let's see if we can move on. We're going to once again show you here. We're going to begin a new layer, and then we can go here, import a layer image. This time 3, 4. That's not it. Edit, undo, file, import a layer image. 2, looking down here, 1, 2, 3, 4. Let's see if we can bring that in. And now we have this next one. Pretty straightforward. Realize you have two 55 gallons, right, of water. Now 55 gallons is, let's see if we can go ahead. And we're going to go to a new layer. Okay, now we're back to here. So 55 gallons is 110 gallons times what? 8.34 pounds per gallon, and that's going to get your weight here. Simply supported beam. Subject to, with the span of 20, subject to a point load, not a double hatch, a single hatch, which is equal to somewhere around 834 plus 83 is about 910, thereabouts. Now 910 is going to have you push up here, thereabouts, with about 455. So what is the internal reaction moments? We now are going to walk to the quarter point, 5, and we're going to cut a free body diagram. And we know with that, you've got something there. You're going to cut a tension, a moment, and a shear. Obviously, the shear here is equal to 455, and the moment is going to be equal to 5, which is the distance from the quarter point, 5 times 455. And when you think about it, since this is symmetrical, you know it's also got to be the same over here. So the moment at the two quarter points is equal to 5 times 455, and the other one is, of course, is going to be 10. So there's two of these, and then it's 10 times 455. Why? Once again, you showed the reactions. You walk backwards until you were just on the inside of that. That's 10. And you said, what's behind us is not important. And you realize that if this is 455 out of 10, the moment is going to be 0.4555. So that's how you do a problem like that. Recognize the quarter points. And if here the internal coordinates, we cut this off a little bit. It is supported as a cantilever, and it is 10 meters. I'll work it this way. So the span here is 10. Internal moment of the beam is basically off here is 1,000 liters. In other words, it would weigh, the weight would be 9800, 9.8 times 1,000, but it's going to weigh 13.6 times that for newtons. And the moment is just going to be, if you think about it, we're going to cut it off here, replace this with this, and this. And if this is 9,800 times 13.6, the moment is going to be a negative 9,800 times 13.6, because 13.6 times as great. So this is what? 1,000 times 9,800 times 9.8 is 9,800 times 13.6, and that is the value of the internal moment. Okay, we skipped now a couple of ones that were before this, which were the problems that were in fact the method of joints, method of sections. So, but learning to very quickly solve your reactions and then figure out what's behind you not being important becomes incredibly important. Then also realizing very often that you can do some pretty easy guesses if you just learn the simply supported and the cantilever. I'm going to now move on. I'm going to go once again to this problem. I'm going add a new layer. I'm going to import a layer image, and then we're going to finally go to 5, which is 9 and 10. Okay, open web joist. First off, okay, we got this. There we go. All right, open 6 feet between joists. So if you're thinking about here, this span, right, you're going to have, there's one, and there's another one, and there's another one. From here to here is 6, which means 3 feet goes to each one. So you have then in effect something that's spanned out. The span is 50 feet. The load is 600 equals 600 pounds per lineal feet. You know that the maximum moment occurs in the middle, but you don't necessarily have to do that. 600 times 50 is going to be 30,000, or 15 kips here and 15 kips there. 15 kips there and 15 kips there. Let's double check that. 6,000 times 5 is 15 kips. Now, if you cut the cross section at mid-span, what are you left with? Well, you're left with out here 15 kips. And of course, halfway there, you're also left with 15 kips. And you end up with a maximum moment equal to WL squared over 8, which is of course 600 times the span is 50 squared all over 8, and that gets you maximum moment. But now you think about that maximum moment occurring here, and what do you have? You have two forces, compression and tension, if you would, and they are 5 feet apart. So you once again divide that by 5, and that gets you what the force is in any one of those. Again, we'll work these out, but this kind of sense of what the intuition is and how you quickly go through with these that general sense, you see how quickly and how often that WL squared over 8 equals the tension times the sag concept is going to come back at you. We'll finish out here now. Equivalent uniform load is in kips for a load that's applied at the unit mid-span. That big W in this case is 20 kips. Remember, you're going to need to take this. If it's 10 at the middle of the span, it's the same as 20 spread out. If it's uniform load applied at the first quarter point, you're going to go from the factor, if it's 20 here, and it'll be 0 there. This one is going to be 10. Now what you end up doing, however, is learning to, on that first one, putting in that 10 there. I'm going to run out of space there. And of course you get 5 there and 5 there. Figuring out what that moment is, it's 5 times mid-span. And then realizing whatever that load is, maximum load is equal to WL squared over 8. And you kind of go back and do some of that. So this intuition here of having double at the middle, nothing at the end, and then sliding something like that, that's something called an influence line. All right, so I'm going to post this one out, and I'll put the exam solutions up, written more generally and correctly after I do them tomorrow and grade out the papers. You'll then want to remember some of the basics of this, that in fact there's really not that many problems there, or ways to do problems. One is this concept of putting in your known directions into a matrix, and on the other side putting the opposite of the knowns over here. So your unknowns over here times your matrix, tension 1, tension 2, or tension 1, 2, and 3. And the other one is learning to walk behind you, walk backwards, cut a beam, replace it with a requisite number of unknowns, and say what's behind you is not important. Or in fact, on a truss, the same thing. Cut a truss and replace it with the requisite number of unknowns and look at the sum of the moments equals 0 if it's joints, or sum of the forces, sum of the moments equals 0 if it is a section problem, sum of the forces equal to 0 if it is a joints problem. Thanks for listening.